Hello, my name is Lee Presser. This is my show. I speak frequently to very interesting people. Some of these conversations are so exciting, so intellectually stimulating, I thought others might like to listen in. This is the reason we started recording Conversation with Lee Presser.
Welcome to Conversation with Lee Presser. The autonomous car, the unmanned aerial vehicle, and human-like robots are 21st century reality. Amazon expects to deliver products to your home using a drone. Google's designing a car which will pick you up, deliver you to where you want to go, and wait around the corner until you tell it to come get you. These are things that were designed by engineers. Our guest today is Dr. Brad Noble, Associate Professor in the Department of Electrical and Computer Engineering at Southern Illinois University at Edwardsville. His specialties include embedded systems, computer architecture, sensors and interfacing, network engineering and security, parallel and distributed systems, and signal processing. He joined the university faculty in 1996, has taught 18 different subjects, and has been the recipient of both the SIUE Teaching Excellence Award and the SIUE Alumni Association Great Teachers Award. Recently, he collaborated with Dr. Mike Shaw in the chemistry department. As a result, SIUE was granted a patent for an instrument fundamental to the field of electrochemistry and is essential for battery and fuel cell research and design. Dr. Brad Noble, welcome to Conversation.
Good morning.
So, that was the most interesting part there at the end, was this
potentiostat.
Yes, I didn't even try to put that in there. I was going to let you. So what is a potentiostat, and what is it that's so great that it needs to be patented?
Potentiostats are kind of fundamental to electrochemistry. Now, people don't normally hear the word electrochemistry, but they use it all the time. Any battery-powered device is electrochemical. You're storing energy in chemical bonds.
Like your car battery.
Your car battery, the cell phone in your pocket, all of that. And, large power devices, things that we need power plants for, they require power to be produced as it is used.
Right.
But with things becoming more intelligent, the subject of this program, we have to have the ability to store this energy and hold it for long periods of time and then be able to recharge.
Which is hard.
It actually is. The amount of energy stored in your phone battery is really incredible. In fact, there's some YouTube videos of people doing very dangerous things which are intentionally causing to release that energy abruptly. And it's explosive. There's a lot and the most recent thing, what was it, last year, the so-called hoverboards, that they're banned on so many things. Intrinsically, there's nothing wrong with those devices, but the way they were made, they weren't designed properly. And so the charging circuitry and the type of and the battery design wasn't done right. And so the manufacturer, a lot of them made in China, didn't design it properly, and they would catastrophically release energy, resulting in fires or explosions. And
we've heard of stories of people that had a cell phone in their pocket, and next thing you know, their leg is burnt severely.
Absolutely. You have to realize that the amount of energy stored in a battery, doesn't seem like much. People think batteries, they think AA's, AAA's, something like that. But to power a device over a long period of time, especially if it has a motor in it, which is more demanding on the amount of energy requirement, that's a lot of energy packed in one place. So potentiostats are used in battery design. So you have your anode and cathode of different material, you have an electrolyte, and then you look at the potentiostat can measure how is the energy put into the chemical bonds, how is it brought out of the chemical bonds, and then when we recharge it, how much of those chemical bonds are recreated, thereby putting energy back in, how many of them form an irreversible reaction where that limits the life of the battery because you can't completely remake all the bonds. And that's one of the primary applications where they're used for. The reason why Dr. Shaw and I pursued the patent was they're very expensive. Cheapest one on the market was $6,000, typically $20,000 to $40,000.
The devices that already existed.
The devices
when you started working.
Yeah, and that's what Dr. Shaw works with. He's an electrochemist. And over coffee, we just started talking. I thought, well, hey, let me look at this. Maybe there's a cheaper way to do it. And it took about 5 years, but I've come up with a design that we actually have a company in St. Louis that is in the early stages of making the first commercial prototypes. And they'll probably sell for about $300. And so we're trying to get
better
the price.
Than $6,000, yes.
And they don't do all the things that a $40,000 instrument does, but they do nearly, well, in the words of Dr. Shaw, 98% of anything an electrochemist would ever need. And that's what we're looking for, because we want to get these devices priced so that, for instance, universities can introduce electrochemistry, say for freshman engineers, so that they can actually see how batteries operate, they can test them, they can analyze them. Electrical engineers, for instance, never have anything about battery design in their regular classes, and one of the reasons is the instrumentation is too expensive. It's too specialized. There's 3 potentiostats, 3 or 4 at SIU alone, and that's because they're pricey. But if we can make one that is low enough price, we can get that down there, because energy storage is a big problem in the future. You know, how do we produce it? You know, you think about alternative energy systems, solar and wind farms, and that solar farms, they can store energy during the day. I'm sorry, they produce energy during the day, but if you want to have them power your home overnight, you have to be able to store that energy.
Exactly.
And it takes an awful lot of energy to operate a home.
And lastly, SIUE is actually the patent holder, and you guys just are the 2 of you who designed this. You're sharing with
Absolutely.
With SIU.
Just like an engineer working at Boeing might come up with something that's patentable, their name is on the patent. The inventor's name, only the inventor's names can be on the patent. But as an employee of the university, Dr. Shaw and I, patented it through the university. The university is the patent holder, and the university will license it out, just as Boeing would do.
Right. Okay, so moving on to the main topic of the show, which is autonomous vehicles, things that we used to see like on the Jetsons when I was a kid, probably when you were a kid too, and nobody then saw this anything other than as futuristic comic book kind of. That's way out there, science fiction. But now, I mean, seriously, as I said in the script, they're talking about cars that you can just call up on your cell phone, say, "Come here," and it will.
It's getting there, and it's coming.
And as a matter of fact, I had the head of MoDOT sitting here in that chair, MoDOT St. Louis, and he was saying that it's his belief that in short order that will be the norm, that cars will be the autonomous kinds rather than the driver like we have today.
Short order is a relative term, of course. My belief, it's going to be at least 10 years before you start to see many of them on the road.
That's short.
It is,
That's
absolutely.
short.
I mean, when you're a kid, it's not short. When you get our age, it doesn't, not quite as short anymore. But I don't believe they'll be entirely replaced just because of the psychology of people. Americans have always loved their cars.
I say the same thing. I want to drive.
Americans like their autonomy.
What has happened since I was a kid, where this was just a dream and it was sci-fi, and now all of a sudden they're actually doing it, and it still sounds crazy, but they're actually doing it. Now I see these cars actually do go around.
So one of the things that's happened is there's the main branch of computers getting better. Is fairly obvious to everybody. It's, you wait a few years, go buy a new computer, it's faster, it can store more information, the graphics are wonderful. And as we've been able to get more density of transistors on a chip, we've been able to make more powerful computers. And that's what people see. What people don't realize is there's a second branch of chip technology, computer technology, where as we've been able to get more transistors on a chip, we can take what used to be on an entire motherboard of a computer and pack all of that and more on a chip. And so now you have the power of a computer, say, 10 years ago, which is still fairly powerful. And you can pack that into a really small integrated circuit and battery powered. And now we can have all this computation, all this memory storage. Memory, think about memory. Now,
wait, I got to ask one question though
Yeah.
before we go any further. And I know I don't want a long-winded answer to
Sure.
this, but how do you take a motherboard, which is usually like this, by this, or this, and pack it into a chip?
it has to do with something called feature size. So feature size is the smallest object you can represent on silicon, silicon being the predominant semiconductor that's used.
Is that like molecule level?
We're not quite at the molecule level, but it gets really small. And there's a lot of challenges. It's getting so small that there's significant technical challenges to overcome in order to pack that in there. But it's a matter that the market's there, and for companies, there's a lot of financial incentive to figure out new ways of squeezing more transistors on a chip. And it's through the progression of computers in the same way that all tools progress. If you go back in the history, it took the first hammer made out of rock to make the next hammer that was better. And for computers, they've advanced at a much more rapid pace.
Very.
So,
when you think about the computer that went on Apollo 11 to the moon, which I think was a 386.
Oh, no. The one that took us to the moon, your calculator, your kid's calculator would blow it away in terms of computing power.
Right.
It just...
Well, it got them there and back. That was the good news.
Absolutely.
But
yeah.
we have made such enormous progress. So now you're saying that you've got so much processing power that can be put into these cars.
Into single chip computers, that they're like literally a computer on a chip, right, in terms of what you used to think of as a computer.
Now, human beings, let's face it, I mean, our brain works much differently than any electronic device does.
Absolutely.
We're electrochemical, and we see things different. And we make decisions in different ways. So it scares me to think that a electrical chip is going to be making logic decisions in a different way than I would be making when we're driving along. So how is, I mean, do we have like sensors all over the vehicle that tells the CPU what's going on out there?
So the ability to pack a tremendous amount of computing power in a small amount of space, that's the biggest thing right there that has led to automation. You mentioned sensors. That's the second big advancement that has happened. One of the most significant ones being the accelerometer. Do you ever think about your phone? You hold your phone vertically, and it shows you the screen, and you read vertically.
Right.
You tip it sideways. How does it know that you're holding it sideways? It's measuring gravity. Gravity is acceleration, and there's a chip in there. It used to require gyroscopes, but these are solid-state devices. Yeah, and actually at a very tiny level. I mean, we're talking about millionths of a meter level. It's like there's a block of silicon, and there's a tiny arm, and it can flex. And as it gets closer, it can measure that it's closer. It changes the capacitance. And if you flip it upside down, it tips away, and the capacitance, differs. So for three-dimensional space, we have a 3-axis accelerometer. We have one for X, one for Z, and one for Y. So for your phone, if you hold it this way, then it says, well, gravity's down, I will present it this way. And if you rotate it, and that's why if you take a picture and you're not careful, so you're holding it and you think, oh, I'm going to take a picture on the ground, and then you tip it down and then you rotate, it doesn't know that you've rotated it because it just senses gravity going straight down. So that's one type of sensor that's relatively speaking new.
See, what you just said, that's the scary part. It doesn't know. I mean, you and I know when you're driving a car, especially, I mean, let's face it, when you're an experienced driver, you're watching other people drive. And I'll say to my wife oftentimes, that guy's going to do X. And sure enough, that guy does, and it's dangerous, whatever it was that he was going to do, and he does this X, like pull right in front of you or something, or nearly cause an accident. I don't believe the processor is going to understand to be able to point over there and go like, hey, that guy's going to do something crazy.
Absolutely not. And so when I use the word know, I'm using the word know in a very informal manner. So when we say know in the psychological perspective, we are talking about to be cognizant, to have a deeper awareness, and no computer has ever been able to do it. There are so-called...
There's no how.
There is no how yet.
Right.
That has never been transcended. People have been working on it for a long time. It's the ability, no one has figured out self-awareness. Fundamentally, all computers do what a person has programmed them to do. So driving a car is a matter of taking in, just sitting down. An engineer has to sit down and think. Engineer, computer scientist, and I personally put computer science in the engineering family. It is both part of computer science is the abstract, what is true for all algorithms, in the same way that mathematicians might say, what is formally true following the axiom of mathematics. Computer science says, well, what is formally true following the axioms of mathematics and logic. But then the other aspect of computer science is, now how do we take a description of something that needs to be done and write it as a procedure using whatever programming language there is?
And the point about how do we get the perception of what's going on out there inside the chip?
So how that's done, say you take your autonomous vehicle. If you were to sit down and write down, well, what are all the steps involved in driving, you'd end up with a pretty long list. And it'd probably take you a couple days to get one that's fairly comprehensive, and you're still going to overlook things. You could start with the basic rules of the road that every state has in their handbook. You know, approaching an intersection, you signal so many feet in advance of the intersection. You approach a stop sign or stoplight with a gradual reduction in speed, stopping at the line. That would be taking, you know, that description describes what you would have to program the device to do. Then you have sensors. For instance, in autonomous vehicles, one of them would be literally a camera that the computer watches. And again, this is all algorithm. A person has to write a program to take what is a two-dimensional screenshot, still image, of a three-dimensional representation, and try to infer that white line on the pavement or that octagon up there is a stop sign. And then...
But chips now can understand these things.
Well, again...
I mean, understand in the sense that you have told it when you see these various distinctive marks, most likely it means.
And a person has the job, an engineer, computer science has the job of trying to extract what does a stop sign look like, and not only that, what does it look like in all lighting conditions at night.
I would think that at some point that if we're going to go this way, that stop signs will actually give off a signal.
Ultimately, that would be much better.
They'll have a, what do you call it, RFID chip?
Some form of transmission capability to indicate, hey, you know, by dead reckoning, I'm a stop sign. When I took my driving test, by the way, in high school, I almost missed a stop sign. And it was simply because in the neighborhood, one of the trees had grown and a branch came down and it was obscuring 3/4 of the stop sign, and I almost missed it. And I believe it would be very difficult to write a program.
To get the car that would see it.
Absolutely. And then you just imagine a stop sign that is partially in shadow. So there's a lot of challenges in programming.
Or the person who steps from the curb not at the crosswalk.
So in terms of sensors, there's the camera sensor. Okay, so the camera's looking. There will also be depth sensors. And so a person walks in front. And there's cars now, they've been advertising them, that automatically brake for you in the event that you don't see something in front of you and it applies the brakes. That's a depth sensor there. And they can be, a lot of them are radar based. And it's basically measuring that there's an obstacle there that shouldn't be in our driving path. And so that is another sensor that's put in these vehicles.
From your perspective, you're an engineer. You know, you do design. Would you get in one of these?
Right now?
Yeah. You're hesitant. You're hesitant. It's not like, oh, hell yeah.
Well, you know, I'm somebody that although I work and develop new technologies, I'm not necessarily an early adopter. You know, that there's some people that they have to have the latest, newest gadget no matter what. These are the people that, you know, stood outside the Apple store for 2 days to get an Apple Watch.
Right, that they could have gotten, you know, like 3 days later, just walked into the counter and got it.
Right, I'm the guy that does it if I really need it 6 months later, but first I got to figure out if I need it. And that's the engineer in me too. I'm not going to buy something if I'm not going to have a use for it, you know. So would I get into it? Right now, for me, it would only be novelty. Frankly, I wouldn't be as concerned in the right conditions because, frankly, just the liability that Google's taking on by releasing vehicles like this. They have
They've had a couple accidents already.
That's true, but statistically, though, the accidents they've had are nothing compared to people.
Yeah.
You know.
Well, I have said, considering some of the drivers today, perhaps the computer will do a better job than some of the drivers that I encounter.
Hey, let me ask you a question.
Well, let me say we got about 10 minutes, just so that you know
10 minutes,
we're to that point.
Just real quick. So this is not my original question, but I absolutely love it because it gets people thinking. Let's suppose an alien race showed up, very benevolent, and they said, hey, we will give you a transportation technology. We'll make it available to you, and it will get you across the world in 30 seconds. You can go anywhere instantaneously. And you can absolutely have it. However, about 40,000 people per year will just not arrive at their destination. You won't see them again. Would you step in that machine? Would you use it?
Considering worldwide, I know what you're saying.
Well,
I know what you're saying.
Yeah.
And yes, I mean, people do 40,000 a year won't, well, they'll die.
Roughly
Car
40,000 deaths per automobile accident per year.
Right.
And what is an automobile? You could think of it as it is a transportation machine.
Yes, it
Without
is.
Prior to cars, if it wasn't within horse riding distance, you weren't going to get there in a day.
Well, according to Star Trek, in the early days of transporter technology, some people didn't get to the other end, but
that's
then
right.
they fixed it.
Well, people just don't realize that, you get in any kind of vehicle, you statistically have a chance, of not making it to your destination, let alone being injured.
Even if you're a good driver,
Even
because of the other crazy ones around you that I'm saying.
Absolutely, absolutely. So the thing, it's like whenever there's an aircraft accident, aircraft, but why does it make the news when there's an aircraft accident? Because they're so rare.
Rare, right.
If they reported automobile accidents, the news would be a lot longer than a half hour, and that's all they're talking about.
Right.
So there's a perception associated with it.
Exactly. I mean, every morning, if you watch, the morning news, you'll see lights flashing and the police are out there. Not everybody's dead, but there's huge number, around 70, 270, 55, 44. There's always something going on.
So let's talk a little bit more about the whole automation thing. You mentioned cars, drones. Another thing that's made this possible, say drones, for instance, is very, very powerful magnets. They have a strong magnetic field for their size and their weight. Neodymium magnets, in particular, have allowed the use to make very powerful small motors, lightweight, powerful small motors, and so that allows us to have these drones that the very weight of the drone itself doesn't prevent it from lifting itself off and carrying a load. And again, the same sensors. If you want to have a drone, something that's going to hover, and if you got four rotors or 6 rotors holding it up, then what's the computer doing? It's measuring the accelerometer. By the way, there's another type of accelerometer. It's a solid-state gyroscope, and it measures pitch, yaw, and roll, and so it can hold stationary. And so it adjusts the speed of the motors to maintain level flight. You want to go forward, then you tip, so just like a helicopter, you tip the blade and you go forward and you go back. But it really comes down to the same thing, that all these automated type systems, it's a computer. And instead of a computer like a desktop, it's a chip computer, lightweight, small, batteries that can hold the charge to let it run by itself.
I noticed that in UAVs in particular, military led the way because one, they were able to get budget, and two, there's a lot of military uses for unmanned vehicles.
Well, there is, and fighter plane technology, by the way, has years ago exceeded the limits of the human body.
I know some pilots that'll disagree and want to be in control, just like I want to drive, but you're absolutely right that the plane of the future may not be capable of carrying a human being because the human being is too fragile.
Well, your warplanes, the maneuverability is the thing.
What's going to Mars? You got to go through all those radiation belts.
Not just radiation belts, just even in outer space, you're hit by the solar wind, which is really high energetic particles. It has
and Mars is cold. People just don't get it. I mean, on a warm day,
well,
it's like freezing winter here.
Well, in terms of automation, just think about what NASA's done with the
rovers.
The rovers,
Yeah.
Spirit, Opportunities.
Out there
Opportunity's still going.
For years, they were like scheduled for literally months, and they're still going years
Opportunity
later.
was made for 90 Martian days, which are each Martian day is slightly longer than a little bit longer than the Earth's, and it's still going. And here's the thing too, there's not somebody at NASA driving the thing real time. The communication time to send a signal to those devices is so long that it has to be autonomous enough. So if they say drive here, when it starts navigating, it has to be able to identify a potential, say, ledge or too steep of a point or a rock.
Don't get caught.
Don't get caught. Stop. And if you can't figure out a way around it, stop and send a message back saying, what do I do now? And when I say, again, we are anthropomorphizing these machines. When we say they think, they measure, no, it comes down to whatever somebody can write down as a set of procedures and instructions.
We got about 5 minutes now.
All right. So
there was something you wanted to talk about, too.
Well, one of the things that this automation has become such a part of modern life that the universities are adapting to that. So in the late 80s, early 90s, as computers advanced, computers are made out of hardware, which is the electrical engineering domain, but they run software and programming, and that's the computer science domain. And there was a recognized need that we needed people who were experts in not all of electrical engineering, but in the computing aspect in particular. And how do we physically build them, the transistors that are used, all the we represent data as an electrical quantity or a magnetic quantity? And then how do we have to program it? So a new degree was made, and that was the computer engineering degree, where computer engineers take roughly approximately two-thirds of the classes in electrical engineering, and one-third of the classes are in computer science. Your classic programming, algorithms, data structures, so you get people that are experts at computers, not just in their physical representation, but also how you use them. The same thing's happening now with more and more universities making a new degree, which is a hybrid between a mechanical engineering and electrical engineering. And it's got the name mechatronics, mechanical electronics, where you have people that have to know, I've got to have a motor out here, I have to have a robotic arm that picks something up, and so I need all the knowledge of the kinematics of motion and levers and bearings and all the other facets to move something, but also the electric technology to know, and I have to read a sensor that tells it how to move or where to move, and I have to drive the motor, so how do I electrically control the speed of the motor and all that? And SIU actually just this last year has a new major, mechatronics.
Is that like rare?
It's growing. You know, computer engineering was kind of rare in the late 80s, and now it's pretty standard. We've had computer engineering since, as an official degree, I'm probably going to be off by a couple of years, around 97, 98, I believe.
So here in the last couple of minutes, I guess what's next? I mean, we're already talking about things that are already in the news, and they're already designed, they're sort of working. What do you see, or what are engineers talking about that's like the next big thing or the next couple of big things that might be possible?
Well, that's always tough to try to prognosticate the future in that. But there's going to be more and more automation.
Are they ever going to have a battery that actually does what they said it was going to do back in 1973? You know, it's going to be able to drive a car around. I mean, I've had people from corporations talking. Everready was sitting here telling me, it's still off in the future. You know, it's all every 5 years. It's still 5 years away.
Right, and you know, there has to be a major, significant revelation or understanding or breakthrough in order to yield significant changes. You know,
some kind like you goes like, oh, right.
Well, sure.
At someday, you know, just like the device that you patented, somebody's going to go like, oh.
Well, and what do engineers rely on? We rely on the scientists to make the discoveries, and engineers go, hey, wow, I can do this now. Something that used to be impossible is now possible. There's going to be some unintended consequences, you know, to some of this. A prediction I made a few years ago, just wild prediction. 10 years from now, McDonald's is going to be replacing their fry cooks with fully automated fry machines.
I'm betting it's going to be less than that.
And it probably will, you know, and because you can reduce what it takes to cook a hamburger down to a set of instructions. You can. That's what recipes are. And now we have the sensors to look at the burger and look at its doneness, infrared sensors to measure its temperature. And that's going to be that's for another show, but that's going to be another facet of it.
That will be. Thank you very much. It's way too fast.
Oh, yes. You're most welcome.
Bye-bye. Brad Noble, he's a professor at Southern Illinois University in the School of Engineering there. We've had a very interesting discussion about, I was going to say the future, but it's actually now. This is going to be uploaded to YouTube. So if you want to show it to your friends, just look up Conversation with Lee Presser, Brad Noble, you'll find it. Thanks. Goodbye. See you next time.